Gas exchange occurs between the lungs and blood and the blood and tissues. External respiration is the diffusion of gases between the blood and the lungs, whereas internal respiration is the diffusion of gases between the blood and the tissues. Both processes are subject to the basic properties of gas and the composition of alveolar gas. Beginning with the basic properties of gas, we will first start by examining Dalton's law of partial pressures. It says that the total pressure exerted by a mixture of gases is equal to the sum of the pressures exerted by each gas. Partial pressure is the pressure exerted by each gas in a mixture and is directly proportional to its percentage in the mixture. The total atmospheric pressure equals 760 millimeters of mercury. Nitrogen makes up about 78.6% of air. Therefore, the partial pressure of nitrogen, or Pn2, is calculated by multiplying 0.786 by 760 millimeters of mercury, which equals 596 millimeters of mercury that is due to nitrogen gas. Oxygen makes up 20.9% of air, so its partial pressure is 0.209 multiplied by 760 millimeters of mercury, or 159 millimeters of mercury. Air also contains 0.04% of carbon dioxide and 0.5% of water vapor, and insignificant amounts of other gases. At high altitudes, the partial pressures decline, but at lower altitudes, like underwater, partial pressures increase significantly. Henry's law concerns gas mixtures that are in contact with liquids. It says that each gas will dissolve in a liquid in proportion to its partial pressure. At equilibrium, partial pressures in the two phases will be equal. The amount of each gas that dissolves depends on both solubility and temperature. For example, carbon dioxide is 20 times more soluble in water than oxygen, and very little nitrogen gas dissolves in water. Also, as the liquid's temperature rises, solubility decreases. A clinical example of Henry's law is a hyperbaric oxygen chamber. These chambers contain oxygen gas at pressures higher than 1 atm, and they are used to force greater than normal amounts of oxygen into the blood of patients suffering from carbon monoxide poisoning or tissue damage following radiation therapy. Breathing oxygen gas at 2 atm is not a problem for short periods of time. However, oxygen toxicity develops rapidly when the partial pressure of oxygen is greater than 2.5 to 3 atms. Excessively high oxygen concentrations generate huge amounts of harmful free radicals, which result in central nervous system disturbances, coma, and even death. The second part to this equation is that is the composition of alveolar gas. Alveoli contain more carbon dioxide and water vapor than atmospheric air, because the gas exchanges in the lungs allow oxygen to diffuse out of the lung and carbon dioxide to diffuse into the lung. Also, the conducting passages humidify the air. And lastly, in each breath, the newly inspired air mixes with the air left in the passageways between breaths. Table 22.4 compares the partial pressure of gas in the atmosphere versus the gases in the alveoli. The take-home message from this illustration is that in the alveoli, there is less nitrogen. You can see the partial pressure is much less nitrogen and less oxygen. But there is much greater carbon dioxide and water vapor. External respiration is the exchange of oxygen and carbon dioxide across respiratory membranes. This exchange is influenced by partial pressure gradients and gas solubilities, the thickness and surface area of respiratory membranes, and the ventilation-perfusion coupling, which is the matching of alveolar ventilation with pulmonary blood perfusion. There is a steep partial pressure gradient for oxygen gas between the blood and the lungs. In the venous blood, the partial pressure of oxygen is 40 millimeters of mercury versus 104 millimeters of mercury in the alveoli. This pressure gradient drives oxygen flow into the blood. Equilibrium is reached across the respiratory membrane in about 0.25 seconds, but it takes red blood cells about 0.75 seconds to travel from the start to the end of a pulmonary capillary. This time difference ensures that adequate oxygenation occurs even if the blood flow increases by 3 times. The partial pressure gradient for carbon dioxide is less steep, with the partial pressure of oxygen in the venous blood being 45 millimeters of mercury versus 40 millimeters of mercury in the alveoli. Although the gradient is not as steep, carbon dioxide still diffuses in equal amounts with oxygen. The reason for this is that carbon dioxide is 20 times more soluble in plasma and alveolar fluid than oxygen is. Figure 22.19 illustrates the pressure gradients that promote gas movements in the body. At the top of this figure, we see the pressure differences in the inspired air versus the lungs. Because the alveoli have a lower partial pressure of oxygen than the inspired air, oxygen flows into the alveoli. And because there is a greater partial pressure of carbon dioxide in the alveoli than the inspired air, carbon dioxide leaves the alveoli. When we look further down in the illustration, we see how the partial pressures of gas facilitate internal respiration. There is a large partial pressure of oxygen in the blood vessels entering and leaving the tissue, and a lower partial pressure of oxygen in the tissue. So, oxygen leaves the blood and enters the tissue. The partial pressure of carbon dioxide is greater in the tissues than in the blood vessels. Therefore, carbon dioxide leaves the tissue and enters the bloodstream. Figure 22.20 shows how oxygen loading into the blood only takes about a third of the time the blood is in the pulmonary capillary. This shows that even if blood flow increases significantly, the blood would still be able to be oxygenated sufficiently. The thickness and surface area of the respiratory membrane also affects external respiration. Respiratory membranes are very thin, and the surface area very large. The thickness of the respiratory membrane increases dramatically if the lungs become waterlogged or edematous, as seen in patients with pneumonia or left-sided heart failure. The 0.75 seconds that red blood cells spend in transit through the pulmonary capillaries may not be enough for adequate gas exchange. The result is that the body tissues suffer from oxygen deprivation. In patients with emphysema, the walls of adjacent alveoli break down, enlarging the alveolar chambers, but drastically reducing the alveolar surface area. Also, tumors, mucus, or inflammatory materials may reduce the surface area. This blocks the gas flow into the alveoli. Ventilation-perfusion coupling was the last influence on external respiration. Perfusion is blood flow reaching the alveoli. Ventilation is the amount of gas reaching the alveoli. Ventilation and perfusion rates must be matched for optimal efficient gas exchange. Both are controlled by local auto-regulatory mechanisms. The partial pressure of oxygen controls perfusion by changing the arterial diameters. The partial pressure of carbon dioxide controls ventilation by changing bronchiolar diameters. How pulmonary arterioles change in relation to oxygen levels is the complete opposite mechanism that we see in tissues. Excuse me. When the alveolar oxygen level is low, the pulmonary arterioles constrict. And when the alveolar oxygen is high, the pulmonary arterioles dilate. This directs blood to go to the alveoli where the oxygen is high, so blood can pick up more oxygen. Remember, the complete opposite mechanism is seen in the systemic system, where the arterioles will dilate when oxygen is low, and they will constrict when it is high. Changing diameters in the local arterioles and bronchioles synchronizes. Let me go back. Sorry about that. Where the changes in oxygen partial pressure affect the pulmonary arterioles, changes in the partial pressure of carbon dioxide cause changes in the diameters of the bronchioles. When alveolar carbon dioxide is high, bronchioles dilate. When the alveolar carbon dioxide is low, the bronchioles constrict. This allows for rapid elimination of carbon dioxide. Changing diameters of local arterioles and bronchioles synchronizes ventilation and perfusion. Ventilation-perfusion is never balanced for all the alveoli because regional variations may be present due to gravity and airflow, and occasionally alveolar ducts are plugged with mucus, causing unventilated areas. Figure 22.21 illustrates ventilation-perfusion coupling. On the left, we see a mismatch of ventilation and perfusion where there is a decreased ventilation and/or increased perfusion, causing a local increase in the partial pressure of carbon dioxide and a decrease in the partial pressure of oxygen. The oxygen autoregulates the arterial diameter, resulting in pulmonary arterioles serving those alveoli to constrict. This matches a lower ventilation with a lower perfusion. When ventilation is greater than perfusion, seen on the right side, this causes a lower carbon dioxide partial pressure and an increased partial pressure of oxygen. The oxygen again autoregulates the arteriolar diameter by dilating the pulmonary arterioles serving the alveoli. This results in increased perfusion to match the increased ventilation. Internal respiration involves capillary gas exchange in the body tissues. Partial pressure and diffusion gradients are reversed compared to external respiration. Tissue oxygen levels are always lower than arterial blood oxygen levels, 40 versus 100 millimeters of mercury, so oxygen moves from the blood into the tissues. Tissue carbon dioxide levels are always higher than the arterial blood carbon dioxide levels, 45 versus 40 millimeters of mercury, so carbon dioxide moves from the tissues into the blood. And the venous blood returning the heart has an oxygen level of 40 millimeters of mercury and a carbon dioxide level of 45 millimeters of mercury.